The title of my talk is Do They Deliver? Practical Load and Security Testing of Cloud Service Providers. And as it is, okay, this is a short introduction of my company, where I work, of ENW, which is located in Heidelberg. We are a small security consulting company. We are also organizing another conference, and our focus is on corporate security in very large and international environments. And in these environments, we also came to do some research on cloud security, and we're giving workshops and stuff like that. And in the course of this activities, this talk kind of developed. And as it is stated here, we have some war stories to tell. The first part is a presentation of load testing results. So people kept asking us during the workshops, what are the real benefits of cloud computing, and do they deliver what they promise when speaking of cloud service providers? And the second part is some results of penetration tests of cloud service providers or applications hosted at cloud service providers. Before this main part, of course, I want to give a short definition of cloud computing. I will come back why this is important, and of course a short motivation why this topic is worth to deal with. And even though it's a collection of war stories, there are quite some lessons to learn when you want to use cloud-based services or deploy your IT infrastructure in a cloud computing environment. So we always try to abstract from concrete stories to more general lessons that can be applied on a broader scale. So I want to start with a definition of cloud computing. This is usually a slide you see in any talk on cloud computing or cloud security, because it's by now the only visualization of the most accepted definition of cloud computing. This definition is given by the NIST. I think most of you guys will be familiar with the NIST and their guidelines. And I'm actually not that happy with the visualization which is provided by cloudsecurity.org, which is not stated on this slide. I don't know why. But anyhow, this is a rather formal definition, kind of academic approach. So I usually go another way. Who of you has already started any instances in any cloud service environment? Okay. 4 people? Okay, and I mean these are 5? Okay, still not that impressive. And I mean, basically most of us are using any kind of what is called cloud-based services. Like, I assume almost anybody has a Google Mail account, whether you use it or not. But still, I want to come to some more concrete examples what cloud computing actually means, besides this definition, and then I will come back to this definition. This is the user interface of the Amazon EC2 web interface, the management interface, where you can click on this button, and then 8 clicks later you have a fully functional virtual server running. And those 8 clicks take you maybe 30 seconds, and then another 20 seconds, and your instance is running. You have a public IP address, you have a full-blown Linux or Windows installation where you can log in. And by the same 8 clicks, you can also start 20 instances of the same machine. So this is one example how cloud computing works. And I usually give this example because many people are not familiar with the term cloud computing. Anybody has heard it, but when we ask during our workshops we give on cloud computing, we hear stuff like, oh yeah, cloud computing, that's this stuff on image processing and editing in the internet, because they are referring to a commercial of Microsoft, I guess, where they offer such a service. Or even more interesting, there are also services like cloudgirlfriend.org. You can register there, and for I don't know how many bucks per month, a girl keeps posting to your Facebook wall or writes you messages on Twitter and pretends to be a girlfriend. So this is obviously not really related to cloud computing, even though for some people this might be an interesting service. I don't know. Actually, I heard on this on the radio, so don't get wrong ideas here. Question, sorry? You have a link? And I don't know if it's cloudgirlfriend.org. That's what I heard. So I'm not sure if it's correct, but I think Google will help you if you're in need. All right, these are examples why it is important to define cloud computing before we talk about security implications of it. So basically, this is a short spoiler for the definition. What Amazon is offering here in its Elastic Compute Cloud, the EC2, is infrastructure as a service. Such as infrastructure, you get a virtual server that you can completely operate by yourself. You can log in, you have root access or administrative access, and you can do whatever you want with this instance. Another cloud offering is the Google App Engine. In the Google App Engine, you have a so-called platform as a service environment, and you develop your applications using a well-defined API, which is provided by Google. In terms of Google, it's typically Java or Python applications with special API calls that you can use to access the user authentication service or the data store. And when you have developed that application, you upload it, and your application is hosted in the same environment as Google Mail or Google Calendar is hosted. You don't have to deal with the operation system level. It's just important that you develop your application, and Google takes care of all of the other stuff. So these are two typical cloud service offerings, and based on these okay, seems like there is a slide missing, so I go back. Based on these two examples, I want to explain this definition a little bit more in detail. So the downmost layer shows some deployment models. Basically, the two on the left are important for us, which is public and private cloud environments. So public cloud computing is what Google or Amazon offers us, a platform where anybody can log in and use the resources as long as they pay for it. All customers are served on the same hardware. Every customer is treated equal to other customers, and you get the same service as any other customer. And it's the most important thing, it's open for anybody, and you have no idea whether your services are run on the same hardware as the services of a market competitor or whatever, or your data is hosted next to the data of a market competitor. The opposite is a private cloud computing environment. Private means that the cloud computing environment is operated exclusively for one customer. This does not necessarily mean that it's operated by one customer. There are also cloud service providers which offer the service to operate a private cloud for customers, and then you use the hardware exclusively, you have your own storage, and nobody else is using your computing resources. I will come back to this, why private clouds are pretty interesting from a usability perspective. I mean, we have already seen the Amazon web interface, and I think it's quite comfortable to have such a functionality like doing 8 clicks and then having a full-blown Linux server running. I said I don't like this visualization that much because it's supposing that there are real layers in a technical meaning, which they aren't. So these layers are just a visualization of different characteristics of cloud computing. So the middle layer shows the service models which are offered by cloud service providers, which are infrastructure as a service, platform as a service, and software as a service. I think most of you have heard about this. So infrastructure as a service is providing virtual servers, virtual operating systems that you can use. Platform as a service is providing an API. You develop your own application and then upload it to the cloud service provider, who is then running this application in an environment by his choice. You cannot influence this environment. And software as a service, in turn, is just using software which is hosted on infrastructure and a platform as a service layer. This is an important fact usually. Actually, this layer is layered by itself. So any platform as a service, cloud service provider uses infrastructure as a service services to host his offering. And all software as a service, or most software as a service offerings are based on platform as a service, which again is based on infrastructure as a service. So within this middle layer, we have indeed a layered architecture. Any of these offerings can be offered in a private cloud or a public cloud, so there can be arbitrary combination of between these different layers. It's not like there's a strict assignment of service models to deployment models. But the most interesting part are the essential characteristics which are proposed by NIST for cloud computing environments. We have 5 characteristics which have to be fulfilled by any cloud computing provider who wants to be called a cloud provider or anything with cloud in its name. So, on the left side we have broad network access. I think this is pretty obvious. Your data is hosted in a foreign data center. So both the data center and the client needs a broad network connection to be able to access his data in a usable way. Then we have rapid elasticity. This is one of the more important points. Rapid elasticity means you can scale up your resources quickly up and down, like launching another 20 Amazon instances within seconds if you need it. And if you don't need it, you can scale it down. This is closely related to the term pay-as-you-go, which is also often cited when talking about cloud computing environments, which is not included in these essential characteristics. The next one is measured service. Of course, the cloud service provider must be able to measure the resources you have used to be able to bill you. In turn, this provides quite good feedback about the resource usage your cloud services have. So this is kind of a win-win situation. The cloud service provider monitors for billing, and the cloud customer gets quite good statistics about resource usage, like processing power or bandwidth. Then we have on-demand self-service. All of these other parts also apply to classic hosting providers, maybe. So the on-demand self-service is quite important. You have management interfaces, like the one of Amazon. You can do 8 clicks by yourself. You don't have to call any operator in the data center, or you don't need human interaction. You even don't need to click. You can also run a script. And you can configure your cloud computing environment just the way you want it. And the most interesting part is resource pooling. This is related to the economies of scale. Cloud service providers are able to provide you good offers on computing capacity because they pool their resources together and thus increase the utilization of their hardware and thus have less spare capacity, which is a cost advantage, or at least an often cited cost advantage. Related to this resource pooling is the concept of multi-tenancy. I was also already talking about this when talking about public cloud service providers. Multi-tenancy means that on the same hardware, different customers are operated. So these different customers are isolated by different controls like virtualization, or on the storage system on different access control mechanisms, access control systems, on the network layer using kind of private VLANs or something like that. So this resource pooling is closely related to isolation and to the multi-tenancy concept. So given this definition, I also want to talk about a short motivation why it's important to deal with cloud computing. Of course, cloud computing is an emerging new technology, and it introduces kind of a new central computing paradigm. If you use cloud computing, you have decreased cost and improved availability. At least this is what the sales guys tell you when they want to convince you to move your services to the cloud. And this works quite well. I mean, during our cloud security workshops, we would like to say, okay, don't use the cloud for sensitive data, because that would be a good advice in many cases. Of course, it depends on the concrete situation. But usually, some managers already decided, they heard the sales guy spoken, and they know, okay, we can reduce our IT costs when we go to the cloud, so let's do this. Almost the same for any new technology. So, the main motivation to deal with cloud security or cloud computing is, do they deliver all of these promises? And that's why we performed some load tests. Partly on behalf of customers because they were interested, what are the real benefits. And of course, we wanted to be able to give our customers valid feedback about the scalability possibilities of cloud computing environments and how they perform usually. Now this is the first part. As I said, do they deliver the scalability that they are promising? I mean, when we think about the essential characteristic, scalability is not part of it. So still, our customers usually refer to kind of scalability or availability when they talk about cloud computing and what they want to get out of it. So the first question is, do they deliver a scalable computing environment? In doing so, I evaluated 3 major cloud service providers, which are Google App Engine, Amazon Elastic Beanstalk, and Salesforce.com. These are platform as a service providers, and from our point of view, platform as a service is a very interesting offering because it abstracts from a lot of concepts for high availability. You don't have to deal with load balancing anymore. You don't have to deal with data store redundancy and data store scalability anymore. And even more important, there has not been an evaluation of platform as a service performance yet. There have been some evaluation of infrastructure as a service performance, like how well do the Amazon instances perform compared to the Azure instances, even though Azure is a platform as a service environment. But there has no evaluation be performed of platform as a service environments. So coming from the attacker point of perspective, I thought, okay, let's load test these platforms and let's see when they break down. So the first step was to develop an application which allowed the load testing. This application must be able to run on these different platforms, so it was necessary to develop an abstract idea of a small web application, a small web shop application, which offered basic customer functionality like buying products, searching for products, and stuff like that. So, of course, these applications had to be developed following platform scalability best practices. Otherwise, the results would have not been meaningful because they say, okay, you're a bad coder, you did not follow our guidelines. So these results do not really apply to our platform from the cloud service provider point, maybe. And of course, I wanted to provide a comparison to the old world. So I also deployed this application on an old physical server. I will come back to the concrete server later. So there were different challenges in doing so. Of course, as a penetration tester and dirty script coder, it's not that easy to implement applications on all of these platforms following best practices. It was kind of tough work when you're not used to developing. And it was important that the developed platform put load on any component of the platform as a service stack. I mean, infrastructure as a service usually offers you a virtual system, but platform as a service environment utilize different components like load balancers, the underlying data store, the application server itself, and of course the network infrastructure. So the application was developed in a way which allowed the generation of load on any of these different components. Then, of course, it was necessary to develop a stable load testing framework. I mean, there are a lot of load testing frameworks available, but I think you know that when you're developing something on your own, the time to adapt a framework or develop your own set of scripts which do the same almost holds equal. So, using this framework, I was evaluating different cloud service providers. I already introduced them. In terms of latency, so which time does it take for the platform as a service environment to host, to serve the requests of an increasing number of concurrent users. So the load testing framework simulated valid users. One user, for example, does 5 product searches, buys 3 products, deletes his shopping cart for one time. I don't have the concrete numbers in my head, but something like that. This is one simulated user. And the load testing framework simulates 1 concurrent user, then 2 concurrent users, and so on, for a defined maximum number of users. Of course, these users are simulated in parallel, so it was possible to measure the overall time which the platform as a service environment took to serve all of these requests. So, coming to the first result. The first result is of Google App Engine. Google App Engine provides you an environment to deploy your Java or Python application directly into a scalable hosting environment comprising of a load balancer, application servers, and a big data store. They give you feedback how many virtual servers are running at the moment to host your web application, but you have no way to influence the number of applications. This is the way how platform as a service environments usually work. You host your application there, and they take care of all the stuff to provide it in an available and reliable way. So, I simulated up to 50 users on the Google App Engine platform, and we see that the development of the latency up to 50 user increases a little bit more than linear. Still, this is not a bad footprint for our application. More interesting is that we can see that there are some areas where the latency decreases again, and all of these areas can be directly compared to the time where Google started additional virtual instances. If I remember correctly, at the point when 50 concurrent users were accessing the application, I think Google used something like 16 instances to host the application still in an acceptable time. So we also see that the time is increasing. This would have been more equal if the same number of users would have been running for a longer time, because the spawning of instances would have been finished and the instances would have been available to host the application. But still, the development is not that bad. So this is one result. It's not that interesting to talk about it when we have no comparison. So the next result is of the Amazon Elastic Beanstalk. I had a short introduction of the Amazon EC2, the Elastic Compute Cloud, which is the infrastructure as a service offering of Amazon. So the Elastic Beanstalk is a platform as a service middleware, which uses all of the components which are offered by Amazon. So the Elastic Beanstalk combines application servers and database servers hosted in the EC2, and a load balancing service of Amazon, which load balances HTTP requests between the applications. So in case of Amazon, it is possible to define thresholds, like on a CPU utilization of 80%, please, Amazon, spawn more instances to host my application. And you can also configure the load balancing service. So I was mainly interested, how would Amazon be performing when we only have one instance running? So I used the biggest available instance at that time, which was I think it was called 4x extra large instance with like something like 70 gigabyte of RAM and 16 CPU cores. I don't remember the correct numbers, but we have this development. This development curve is basically better than the one of the Google App Engine. We see we have lower response times, overall response times for the increasing number of users, almost no increase up to like 27 or 30 users. Then we have a little jitter, and the latency increases to 60 seconds for all of the users. This would be okay. We have experienced performance jitters in virtualized environments before. There are also papers on it which describe these jitters. But more interesting is the sharp, basically it's a drop when simulating more than 57 concurrent users. It was reproducible that when I simulated more than 57 concurrent users, the Amazon instance became unavailable. So the load balancer answered with a HTTP 503 service unavailable error. And this was reproducible. Any time I simulated more than 57 users, the instance became unavailable. Which is not a big deal. I mean, to serve 50 users, Google App Engine was using 16 instances. So this big instance was doing quite well up to 50 users. but still, simulating more than 57 users, it was possible to crash the application or the environment. When I stopped the test, it took 5 to 6 minutes, and then the environment recovered and became responsive again. So I will not make any overall conclusions here. Let's see how force.com is doing. Yeah?
Would this be a spam prevention measure of sort of like turn off the firewall of the instance?
What do you mean? Kind of an anti-denial of service measure when they see that the load is too high? I mean, that would mean when a customer is hosting a high traffic application in the cloud, Amazon would turn off this instance because there's too much traffic. That's not the idea of a...
If they come from the same IP.
Okay. Still, I do not get really the point. You will see later why I don't think this is true. I have another story on this, and basically I don't think that a cloud service provider who you pay to host your application in an available way should turn off your instances if there's traffic on them.
Well, did you read the terms and conditions?
Yeah, I read that.
They would state something like that, right?
What? Like what? Are you referring to a concrete paragraph?
They
Or?
get the countermeasurements, right? They will put it down in the terms and conditions.
True. I mean, they have something in the terms of condition like we protect against denial of service, but only...
You are not allowed to measure them. That's in the terms and conditions.
Yeah, I mean, that would mean you want to host your application at Amazon, and you're not allowed to perform load testing of your applications.
And you may not publish results of load tests.
I mean, basically, these are load tests of my application, so not of Amazon. Don't get me wrong here. I will come back to this anti-denial of service stuff. We have another funny story later on. So, yeah, the results of force.com, I'm not really happy with them. I mean, basically, this is work in progress. And force.com offers a user interface which is heavily relying on JavaScript. So it's not possible to use my pretty lightweight curl-based load testing framework. So I had to use Selenium. Maybe you know that. It's a web application test environment which utilizes browsers for load testing. There are also commercial services like BrowserMob, which does use Selenium for cloud-based load testing. So I adopted this approach, and due to my limited server-side, client-side computing capacity, I was only able to simulate up to 14 users before the client-side limitations would punch in. I mean, this is an important part. I always monitored the client-side system utilization to make sure that those drop is not because my client cannot handle more concurrent users than 57 at a time. So we have the results of force.com, which are also interesting. Force.com has very poor response times. And we see that even from 2 to something like 6 users, the response times almost double by a factor of 2.5. So these results are definitely not comparable to the other ones because this was using the curl based load testing framework, and this is based on the Selenium results, which is a completely different thing. But also here we can see some decreases, maybe when additional instances are spawned, and there were some other problems. But still, force.com is pretty bad for load testing, so you should have that in mind when you think about using force.com. The more interesting result is that of the physical server. I was using a physical server with 1 GB of RAM and like 2 CPU cores, hosting, I think it was the same Tomcat, I know it was the same Tomcat server version which was running at Amazon. And I load tested the exactly same application that was running on Amazon. And this is the result. I mean, this application, this server was able to handle 70 concurrent users at the same time. I mean, one can say my application is poorly developed, of course, but still we have the direct comparison from the Amazon instance to this local server instance, which is way less powerful than the Amazon instance. We have a a worse scalability development. It's not that bad. It's still below linear, but if you remember the curve of Amazon, it was way better. So this is an interesting result that you have to consider when you want to use cloud-based services. Amazon might not be as powerful for your processing as local instances may be. So this is where this point comes to play, horizontal versus vertical scalability. You can get from these results that I'm saying, okay, you should not use Amazon because they deliver poor performance. This is partly true, as we saw. It depends on the usage scenario. But in case of Amazon, you do 8 clicks, and then you have not one instance, but 5 instances, and an automatic load balancing service. So this is way easier to scale when you go beyond the limitations that you have for your physical servers. And when you have your physical servers, you cannot just, okay, you can turn them off, but you don't get the money, the initial investment back. So this is a pretty important point I want to make. Cloud computing environments rely heavily on what I call horizontal scalability, like many instances which host your application, and not vertical scalability, make the system bigger and bigger. I mean, there's a limit. We all know that, also for Amazon, even though you can get pretty big instances there. So, and each cloud service provider has different characteristics, and you have to address them when you develop your application. You have also to have these characteristics in mind when you want to plan for your load testing in the cloud computing environments. But I will come back to this later in my overall summary. Speaking of Amazon and the ability to have 8 clicks and scale your environment from one instance which hosts 50 users to 20 instances which serve 20 users, still sounds pretty nice. But I guess you have all heard about security concerns in cloud computing environments. So the scalability advantage by management interfaces which allow quick scalability in a horizontal way is one advantage of cloud computing. For me, the term security concerns is way too general, so I was thinking, how could we refine security concerns in cloud computing environments? We cannot have a structured discussion about this when we are not even clear about the concerns that we have. So when I think of an evaluation we did, these concerns become a little bit more clearer. We had an evaluation of a software as a service, cloud service provider. They offered some kind of a human resources management solution, and a customer of us wanted to know from us, okay, we have these 3 cloud service providers, which is the most secure one? So we had to do an evaluation of the cloud service providers, and one of the 3 cloud service providers agreed that we were allowed to perform a pen test. I mean, this is also related to the terms of use. You're not allowed to do penetration testing of your cloud service instances at Amazon. You have to request you have to fill in a request for that service. So you you use a web formula hosted at Amazon, and you submit your request, and then Amazon says, okay, you have 3 days, and you're allowed to pen test your own applications in the cloud. So this is pretty true for all cloud service providers. You don't have much room for contract negotiation. So it was quite surprising that at least one cloud service provider agreed that we perform the pen test. So the target was a human resources web application. I don't want to tell much about the details, it's not important. So our penetration test had to be, of course, a typical web application pen test, including pen testing of the server infrastructure and pen testing the cloud infrastructure, like automatic scaling mechanisms, the management interfaces, the network separation, the separation from other customers. This would have been the second step of the test. So unfortunately, there was no need to perform cloud-based load testing. After 1 day, we stopped the test because we had more severe findings than in most other pen tests, which lasted 20 days or more. So there wasn't a need to perform any cloud-based testing. So one of the main findings was this HTTP put to the web root was possible. So we were able to upload our, I think it were Java files, they were executed, and we were able to compromise the complete application server. I'm not sure when you've seen HTTP put enabled on a web server the last time, but for us this is something like years ago. Such a finding we saw last in the 90s or something like that, but usually people learn that HTTP put is a bad thing, and actually I don't know what is possible to enable HTTP put on an Apache web server. I mean, all of the application servers have this disabled by default. I can only imagine that there were some REST-style services running which usually utilize alternate HTTP methods. But still, this is a horrible security footprint. Another reason for this being enabled might be that there's a short time to market, and anybody wants to do cloud. And cloud is kind of abstracted from the technical concepts. I mean, you do 8 clicks and you have a virtual instance in the internet running with a public IP address. Or you upload your application and it is hosted in a load balance environment. So no need to deal with the technical concepts of this. Still, this is a pretty bad idea to have HTTP put enabled, and it was a horrible finding for us. So I was talking about structuring these security concerns. For us, this meant we have to find another way to ensure security. I mean, the cloud service provider was willing to address these issues. This is maybe an interesting side note. I think 2 months later or something like that, we had a retest. And guess what they did to close the findings that we had? Any guesses? Okay, I mean that would have helped, at least for our pen test. That would also be an interesting choice. Yeah, good idea. No, of course they put a web application firewall in front of it. So all we had to do was to encode the put in another way, and we still had the same finding. But this is only a short side note. Of course, these findings can be abstracted to more general conclusions. We have typical controls that we recommend customers when they have to deal with outsourcing providers, third-party vendors, or whatever. And risk analysis and trust evaluation is usually a part of this. So I want to introduce the system operation lifecycle. This system operation lifecycle elaborates the steps which are necessary to operate a system. For example, you have hardware which is operated by your employees, you have your operating system installed by your own employees, you can harden that operating system, and based on the different colors, these are the areas of responsibility which you can influence. The black ones are basically steps in the operation lifecycle you cannot influence. The cloud service provider is responsible for the steps, and you have to trust the cloud service provider that he will perform these in a secure way. There is no other way than you control these steps. You cannot control the employees of the cloud service provider. You have no custom contracts which can address these issues, and in terms of a platform as a service provider, you cannot harden your operating system, which is used in this platform as a service stack. So I think I have to hurry up a little bit. What the system operation lifecycle is telling us, it's not possible to secure the cloud by all aspects. There's simply no possibility, because these areas, at least these areas, the yellow ones also are under control of the cloud service provider in platform as a service environments. It's just not possible to secure the cloud. So when we look at several risks which are provided by NISA in a comprehensive risk analysis document, these are the main risks in cloud computing environments. And these risks can be directly mapped to steps in the system operation lifecycle. So, for example, loss of governance. I mean, the governance of your data, you can influence them in steps 1 to 30, at least 1 to 9. You cannot influence in a cloud service environment. Same for isolation failure. When you think about patch virtualization, appropriate network separation mechanisms, all that stuff, the network is definitely not under your control. Neither is the storage which is used by the cloud service provider to host your data. And of course, malicious insider is the classical example, even though I would not consider this to be a high risk in cloud service environment. There are other ones which are more relevant from my point of view. But still, you cannot mitigate these risks because you cannot tell the cloud service provider, okay, you do not hire this guy, you only hire this guy. That's not possible. So this is what the system operation lifecycle wants to provide, a short help to structure security concerns. Is this a security concern which we can address, or do we have to trust the cloud service provider? And trust is another important concept which we usually use at ENW. When we cannot control something, you have to trust something to be confident at the end. And this trust is usually based on some trust factors, which you can assess for a cloud service provider as well. These trust factors mean different things. We have the trust factors symmetry and transparency. Symmetry basically means does the cloud service provider trust us? And transparency, are his processes transparent? Does he provide any documentation about his security operations and stuff like that? So basically, transparency and symmetry would be the trust to perform a pen test. If they do not trust us enough to allow us to perform a pen test, this directly affects our trust that we are putting into the cloud service provider. Another relevant trust factor is consistency. So what happened in the past? How did the cloud service provider perform in the past? Were there security incidents? Were there outages like the Amazon outages in, I guess, April and June? And also the past pen test results. So the cloud service provider we evaluated was transparent and also trusted us, but the results from this consistency, from this transparency and symmetry directly affected the consistency of the cloud service provider. And a last part is the value of reward. What do we get out of trusting the cloud service provider? And this can be partly evaluated following the introduced load testing approach that I proposed. So these are basically trust factors, and I tended to put high trust in Amazon at the beginning of 2011 because they had no relevant security incidents by that time. They had no outages. They were very transparent. They had the best security documentation of all cloud service providers, and the prices were really good. So we also had a value of reward. So I tended to trust Amazon at least until the beginning of 2011. So we also had some projects which did not process confidential data, and we used Amazon a lot, and most of our customers were interested in the usage of Amazon. So we have an Amazon account, and in the course of our regular internal password audits, we also audited the quality of our Amazon account password, which is bullshit. We just wanted to see what is Amazon doing when we try to brute force our own account. But still, this was kind of the official statement. We had a regular password audit. So what we are doing was brute forcing the default Amazon login interface. Fun fact, by the way, this is the same login interface that you use to purchase DVDs or CDs or whatever you order on Amazon. So the same user account you use for DVDs, you can also use to order virtual servers or virtual platform services. So even though it was a tricky setup, the minimal password requirements of Amazon were 6 characters, no other restrictions. So we set our password to a 6 number password, 6 numbers, no other characters, and we tried to brute force that stuff. It was not that easy to brute force. I was quite surprised. I didn't do brute forcing for a long time before that. And most current brute forcing tools do not cope well with modern web application authentication mechanisms, like a lot of cookies with different scopes and redirects and stuff like that. So I used the burp suite I think quite some speakers mentioned it, for the brute forcing progress. And even though it's not a tool for brute forcing, it did quite well. We performed on our peak times 80,000 requests per hour. And we had, including some try runs, over 2 days, something like 4 million requests from one IP address. This setup was set up in about 20 minutes. It's described in a more detailed blog entry. And basically, for some hours, we performed 80,000 requests per hour for our account, for our password. We iterated through 0001 to 999999. So basically, it was possible to brute force our password, which is of course not our actual one. We do not use only 6 numbers, even though it's not a productive account. I mean, it's also not hard to anticipate what the brute forced password was, but anyhow. So it was possible to brute force our password. I think that's not that surprising that it's possible to brute force passwords in 2011. The more interesting results was that there was no account logout, no connection throttling, no captcha solutions, and no reaction from Amazon. So no email for us, hey, it seems like your account is being abused or something like that. No reaction at all. So following a responsible disclosure approach, we contacted Amazon and told them, hey, we performed a regular password audit and there was no response from your side. And this was what I was getting. So hello, Matthias. Thanks for contacting us. It's great to hear from customers who are passionate about security just like we are. And then we have noticed that your account has a difficulty in authenticating properly, and we're actually about to contact you. So this is a funny side note. I mean, there's a long part of the email which I skipped because it's more funny when it's put that way. And also, I wrote that email on Saturday. This was the response on Monday, so they were actually about to contact us. Still, to be fair, besides laughing, we had a very good response of Amazon. We had an interesting conversation. They implemented a captcha solution within 2 weeks or something like that. And we re-evaluated it, and at least our brute force attack was not possible anymore. So basically, the Amazon security team did a very good job, at least we thought. But this was the first thing which affected my trust in Amazon. The next one, some days after, I think it was in mid-October 2011, some researchers from the Ruhr-Universität Bochum, Germany, presented a paper which is called All Your Clouds Are Belong to Us. And basically, they were able to bypass any Amazon authentication mechanisms. So this is way more interesting research than doing a simple Amazon brute force login. Still, this was kind of a gray zone, for a legal gray zone for a company like us. And this results completely destroyed my trust in Amazon. I mean, the complexity of the web interfaces is enormous, and basically the web interfaces nowadays are the keys to our data center. If you host a lot of applications at Amazon, the web interfaces are key to our data center. So the overall security posture of web applications is not that good from our point of view. And I'm out of time, so I have to skip this a little bit. But at least I was tempted to believe that someone looked at the Amazon web interface. And if we performed pen tests, we would have recommended them, please implement brute force mechanisms, and please do not implement crypto by yourself, which makes such stuff possible. So this trust was destroyed, and 1 minute of conclusions. Do load testing of your cloud service environments to be sure that they perform as you expected, and adopt the necessary changes in your infrastructures, like using the horizontal scalability and not relying on bigger and bigger systems. I mean, this is the way how cloud computing works. And of course, protect your management interfaces and evaluate a cloud service provider. Thank you.